The talk is on climate, and I think that's hopefully going to be enough, contrast. The talk is on climate, and this is, based on our review of various talks that are on YouTube and so on, this is going to give you unique insight, and I don't want to oversell it, but it's going to illuminate and shed light on a number of theories about climate, issues, claims, etc. So what we're asking you to do up front is to reason with us. We're not here to tell you what's wrong or what's right. We're here to explain things that we have learned through the process of spending a fair amount of time studying this. And you've heard a great deal about human emitted CO2. And you get this dose every week. And it's hard for most people who are going to not spend the kind of time we're spending to understand the reasons of what is really going on. And so I think one of my favorites came out last week, a prediction for the future, said the human race will be extinct in a few decades. Now that's the kind of predictions that you're seeing here. And I think that the public, when asked, if they're asked the right way, they frankly don't see what the issue with climate is, because climate outside today is maybe a little warmer. It's fine. They're seeing things that really say that it's not particularly an issue, which makes these claims, the requirement of these claims, to be even more outrageous. But we're not here to answer each of them. What we're here to do is to essentially impart to you what we have learned. Now, it turns out that being both semiconductor device physics guys, the original nerds, as I was telling David, he's a fellow nerd, by the way, is that is actually a very good fit for climate science. Why? Because we span quantum mechanics, optical phenomena, multivariable systems, nonlinear equations, and computer modeling. We both got our PhDs in computer modeling. So we really span a fair amount, but we also are motivated in this particular talk, this particular project, which has been a 2-year project for us. We've covered a lot of ground here, and you're going to see in an hour, you're going to see a broad stroke across quite a few areas. But we value the science in general, but the scientific method, and I'll be commenting on this as we proceed. And we've gained a great many insights into the state of climate theories and their issues and the people that are writing about them. And I have to say up front, we've not actually agreed with anyone 100%. So we've ended up being a fairly discerning audience for these various theories. So what are we going to talk about today? I'm going to show you in a 3-layer model basically what the website looks like and touch on what we can cover today in a sensible way. Consensus, you've heard about the experts tell you science is settled, everything is done. We know you guys are really driving around, you're really messing the planet. And by the way, those of you who really want to hold your breath through the entire presentation, because you emit 2 pounds of CO2 every day. So you've got to really eliminate some of you. So the consensus is not something we'll talk about here. I'll touch on it briefly. It's covered in extensive form in the website. Climate history, we want to touch on a few things in climate history because that's, as one fellow semiconductor author who wrote a book called The Inconvenient Skeptic said, we have to understand where we are, we have to understand where we came from. So we're going to touch on climate history. Temperature, David reminded me on the way over here, and thanks to David for driving up from Solvang for this event. Temperature is an interesting. So the data that you'll see is that there will be a global average temperature for a month or a year. Now think about that for a second. Does an average body temperature really describe what happened to you, one data point, describe what happened to you last year, for instance? You'd say, well, it's not going to really help me diagnose anything. So there's a lot that's covered on the website, and we're not going to touch on temperature here. But there is a lot to be said about it. So the main thrust, probably most of the slides are going to be, or over half the slides, we'll be talking about the science of climate and CO2 and what things are going on, as well as the IPCC models, which are heavily relied upon in the scientific community. And then we can't leave this topic without also covering a variety of predictions, how data is utilized, the IPCC as an organization, how it was founded, what sort of policies are in place and how good are they, and of course, your favorite and mine, the Paris Agreement. And so I would say to you that the website is probably about 80% done. It's going to be a fairly serious number of pages, so it's geared specifically towards climate, and any entry point, any point that of a person that wants to ask a question doesn't have to do a massive search and figure out what's going on. So I tell you that it's there in some degree of efficacy. So we'll touch on a few of these things in what I think is a fairly comprehensive view into the climate theories. Now, you have to look at Earth and step back and look at a picture of Earth from outer space. It's an incredibly complex thing that we live on. It's traveling 1,000 miles an hour, so you didn't know you were running that fast. As you can see, the place that we were at recently, this is Africa, this is the Antarctica, and the globe, and normally we don't think about this very often, but the globe is 71% covered by water. Now look at you can see the clouds. The clouds vary, according to the longitude, but the clouds can vary 40% to 75%. Now you can see the clouds are white, they're reflecting sunlight, and that's going to be an important element in the talk today. So, but we have to start by looking at the journey of CO2. What does CO2 do to the planet? How does it exist in the planet? What's its history in the planet? And so on and so forth. So this is a key element, building block, in the understanding of the climate theories. And simple stats on atmosphere on the atmosphere in the tropics. If you can't really see probably the eye chart in this display, but there's about 96% of inert gases of N2, O2, and argon. And water vapor constitutes almost about 4%. And CO2 in all its forms in the atmosphere is 0.04%. So this is considered to be a trace gas. But I think one little fun fact here is the total mass of the Earth's atmosphere is 5.4 million gigatons. Now, how to put this into context, it's if you have, what is the per capita weight that each of you is holding up, it's 1 million tons. 1 million tons traveling at 1,000 miles an hour. So this is Earth. So that gives you the context, but it does say how much of a trace gas CO2 actually is. Now this looks like a daunting diagram, but it's actually quite simple, and it's very important in understanding the entirety of climate. If you look at this, this is a carbon cycle. So the carbon actually circulates, as it displays here, it circulates from the various sources on Earth into the atmosphere and back again. Now you think, okay, oil in the ground. It gets burned, you create basically CO2 and a bunch of other gases. So what is actually happening here is that the oil in the ground has actually been through this cycle of going into the atmosphere, coming back, being decayed, going into the ground, being brought up out of the ground and burned. It's gone through the cycle as many as 7 times. So carbon is cycling constantly as we speak. But there's a variety of steps here that are important. Sources and sinks. The ocean is probably the biggest sink and source of carbon dioxide. You can see that the total amount of weight in CO2 in the atmosphere at any one point in time is roughly right now about 750 gigatons. That's the 0.04% that carbon dioxide is in the atmosphere. But you also see that there's exchanges here in the vegetation. And we're going to talk more about that. So as you increase the vegetation, what would you expect to happen? more consumption of CO2 takes more out of the atmosphere. So as far as man is concerned, mankind, we're contributing about 5 to 10 gigatons that gets into the atmosphere each and every year, or an increase of about 1 to 2 parts per million per year. 1 to 2 parts per million. You now are essentially in breathing air out. Your air that's coming out is about 40,000 parts per million. So it gives you an idea that this is really low-level stuff. And not shown, which is never discussed, and you'll never, I guarantee you, never see this in a New York Times article, that 95% of all carbon dioxide is in limestone. Think about that. So we've had a lot of carbon dioxide actually in this atmosphere at one point in time. Now, this is a chart that is important for you to understand because it talks to the amount of CO2 that's human generated. I'm going to use the term anthropogenic, which is the common term associated with human generated. So if I say ACO2, what I'm referring to is that which is generated by mankind that gets into the atmosphere. Now, if you see the green line, well, first of all, the parts per million, you can make that out. This is a trend back from the 50s to almost to 2008. And so it's not up to date currently. But you can see a steady increase in the amount of CO2 generated by the burning of fossil fuels. So that says at the point of burning, you generate this amount of CO2. Now the interesting thing here, and it shows you how complex that carbon cycle it actually is, the interesting thing here is that the actual measured in the atmosphere, the valid, everybody agrees is a valid data point, it's called Mount Loa in Hawaii, measurement of CO2. And that is showing you in the black line something that looks like it's hitting a constant. So that says each year I'm going to increase the amount of ACO2 by 1.5 parts per million. But the amount of fossil fuels that are being burned, which can be estimated reasonably well. So many barrels, so much carbon dioxide generated is a good deal larger than that. So what we're seeing is that the actual amount that's emitted of CO2, the actual amount that gets into the atmosphere is roughly about 50%. But the interesting thing here in this trend is that the value of the CO2, ACO2, is a constant in its increase every year. So that kind of suggests that maybe the increase of the CO2 is not entirely due to man's emissions. We're going to talk about that. So really what I've determined and other studies have determined is that the ACO2, anthropogenic, is about 2 to 3% of the total CO2 in the atmosphere. Let that sink for a moment, because everything you've read is that man's emitting CO2, it goes in the atmosphere, and all of that CO2 in the atmosphere is due to, somebody's car. One of you has a car that emits a lot of CO2. And in fact, that's not what the science, the data actually even says. So what we're seeing is that by a variety of studies, and mine is roughly about 2 to 3% of the total CO2, and is caused by humans. And other studies have said 1 to 3%, and they're fairly extensive, serious studies that have been done. And back up and say, well, okay, so natural causes, you've got oceans that warm in some areas. You've got, as it gets warmer, it emits more CO2. There's a variety of things that are very dynamically happening on Earth to cause this. But one of the things that's really interesting about volcanoes is that it's put out more CO2 than pretty much anything man has done to date. And the interesting data point is that there are 97 volcanoes under Antarctica as we speak. So there's a lot of volcanoes being very active that are below the surface. And you've heard of one that's above the surface rather recently. So 96%, I want to let this sink for a moment, 96% of the CO2 in the atmosphere is due to natural causes. Now, does every climate scientist sitting in the audience that would be hearing this say, gee, I didn't know that? No, they would be fighting this statement. They would be quoting their studies. But I can tell you, based on what we know, this is the case. Now, to put this into kind of a graphic form that's easier to remember, if we took the entire air atmosphere and we piled up amount of rice, you could pile up 85,800 molecules as each represented by a grain of rice. And so that's the all air molecules. You'd have total CO2 would be 32 of the 85,000. And the part that you've contributed is 1 grain of rice in that pile. So that kind of gives you a feeling, okay, now, so we got 1 grain of rice, and so how are we going to really be able to do the things that people are saying that we're doing? One of the other things you might be thinking about, so I want to answer your perceived or future question, is how long is CO2 actually in the atmosphere? And there's various studies that have been done about that. IPCC wants to say that these are the CO2 from whatever cause does not distinguish. Although the carbon cycle diagram I meant to mention that I showed you is from an IPCC document. So IPCC likes to say that actually the carbon dioxide is resident for 100 to 200 years. Some of it will stay there for longer than that period of time. But as you can see in the vertical axes, there's a good many peer-reviewed articles, and as Willie Soon, who's a Harvard professor, you might have heard of him, likes to say, these are not peer-reviewed, they're pal-reviewed. He has a very good sense of humor, as you'll see in some of the videos on our website. So this is clearly, most of what's happening is below 10 years. But one professor that we particularly like indicates that actually is more like 1 year, that it really is more like about 8 months of resident time of CO2. So CO2 goes up and it's consumed rather quickly, more replaces it from the ocean, whatever. So if you do indeed have 10 gigatons of emissions that actually get into the atmosphere, and it lasts for a year, it accumulates to 14 gigatons, or 2% of the total CO2. So those are frisky little 2%ers, right? They are really working hard up there. But the good news is that CO2 is in actual fact a great agent, as you'll see over the next few slides. Now there's been, by the virtue of satellites, there's been an increase of study of vegetation across the globe. And in this case, you get a measure of, over the last few decades, occurring in recent decades, you're seeing an increase of vegetation to the tune of about, 20%, 14%. I think the average is 14%. Now this means that the increase in vegetation that has occurred in these decades is actually equal to the area of the contiguous U.S. area. And so the greening of the globe is interesting. Now let's look at what this means, and I hope you can kind of see this chart. This is rice that's grown in a controlled environment at different parts per million CO2. Okay, and to kind of refresh your memory, that's where we are today. So if you're down here, bad stuff is going to happen. We're going to talk more about that. But if you're here, you can start to get some fairly significant increases in rice production. Rice is the number 3 crop in the world. It's, if you go from 300, where we were in previous times, and I think I've got is about 280, that you're going up to 400, you're seeing rice increase its productivity by 34%. That's pretty significant if you're talking about the number 3 crop. And other crops are comparable. So if you pick, in rice, if you pick the right varietal, meaning one that's probably a little bit engineered, if you will. If you pick the right varietal and you expose it to something in the neighborhood of 700, you can actually increase the rice output by 230%. You now have solved world hunger. You can support the world's population, more than likely. So this is rather good news, I would say, to many people who are concerned about starving countries. But now we want to say, now that we've kind of covered what is the anthropogenic CO2 in the atmosphere, what's the benefits of having CO2 in the atmosphere, even at higher levels, but what does climate history tell us? What do we learn from history? We are a result of history. We have evolved as human beings. And so we're going to look at a period of time that's a rather broad period of time, 600 million years ago, meaning that's where we are today. We're at 0. So this is years before present. And the tectonic plates were shifting to make India around 250. You look at all the human evolution, it's not even really on the scale. It's down here in the bottom right. The globe itself is 4.7 billion years. Water has been on the globe for about 4 billion. So this is a pretty good swatch of data and time period. And I want to point out two curves here. One is atmospheric CO2, which in this particular case got as high as 7,000 parts per million back here in 550 range. And you can see the blue line is actually temperature. And I think at 25 degrees centigrade average temperature, you probably don't have any polar ice caps. Everything is basically in water. So you've got, as you can see from this, the temperature and CO2, there's no obvious correlation between them in this data set. So, that's what we're looking at. So there's also a downward trend for CO2, 7,000. It's been higher than that, actually. It's actually been a good deal higher than that on Earth. But we're on a downward trend in terms of CO2 as it starts to be consumed by, you already know the answer to this question, limestone. So the Earth is trying to, kind of capture and use CO2, but it's also segregating it. It's sticking it in limestone. So that's rather significant. That's a kind of an interesting data point. And today we're, as we said, about 400 parts per million. Now, why is that significant? If you drop CO2 below about 180, plants start evolving because they're starving for CO2. If you take CO2 down below 140 parts per million, you and the rest of us are basically toasted. Life on Earth stops. If you don't have plant food, if you don't have plants in general, you're gone. This is no life. So it came actually pretty close at a point in time. I think it got down to about 180. But it got pretty close to basically not being a habitable planet. So that's a sort of a cocktail fun fact. So let's take a shorter period of time, again on climate history. And you're seeing now 420,000 years in something that is a data set that gains a lot of acceptance within the climate community called the Vostok ice core data. So that's taking ice core and examining the temperature and the CO2. And you're starting to see a little more granularity in the data. It's got some more ups and downs. So you see CO2 on the left-hand side, and you see temperature degrees average, global temperature, average temperature for that area in Vostok on the right-hand side. And you also see two curves. One's temperature in blue, and the red is CO2 concentration. So you look at that curve and you go, God, Al Gore was right. CO2 rises, temperature rises. So really what ends up happening is that CO2 actually lags temperature by about 1,000 years in this data set. Statistical analysis shows that CO2 lags temperature, not by visual examination, but by statistical measure. And this particular cycle of every 80 to 100,000 years is something called the Milankovitch cycle, which is in odds or an alternative explanation to the Earth's climate from something called, I think, Arenas, if I pronounce it correctly, David, you can correct me. So data that says CO2 is actually driving the temperature of the Earth. So now we're getting our first interesting data point that says, really, if CO2 is pretty small and total CO2 lags temperature, are we done now? What is the theory about global warming? So let's continue this exercise. So looking at the sun, because I just introduced a solar cycle, Milankovitch cycle is basically tied to the sun. I want to point to you what the Earth scale is here in the bottom corner, and a sun flare, which is presumably the scale. And the surface temperature of the sun is millions of degrees. Now, any of the photographers here would know that the light that's being emitted from the sun comes in at 5,500 Kelvin. That's the effective temperature of radiation from the sun. That's daylight. You walk outside, you're getting the full range of UV to whatever at a characteristic temperature of 5,500. But this surface is over several million degrees. Plus, you thought, until I told you were wrong, that the center of our galaxy was the center of the sun. That's not true. The sun is not at the center. The center of the galaxy is about 50,000 kilometers away from the surface of the sun. Another interesting factoid. But it kind of plays to the theme here that I'm giving you. This is a very complex system. So many cycles, 10,000 years to 100,000 years. There are several cycles in the cosmic ray category that are millions of years. So there's lots of cycles associated with this. And it turns out that global warming, quotes, is actually being observed on other planets in this time period. That funny, last time I checked, there aren't any humans emitting CO2 on these other planets. But you're starting to see the kind of phenomena, the warming up of the climate that we're experiencing, you're starting to see that on some other planets. Now, the interesting thing to show you the complexity here, and that's all we're going to talk about, just a look quickly at the complexity. If you look at Jupiter and Saturn, they're two very large entities that are further out than the Earth, but their variation in alignment with the sun actually causes the sun to wobble on its axis. So the sun is like a ping pong ball being driven by some kind of air jet. And that really does affect the Earth's climate. Now, if all the climates lined up like this, and it probably occurs maybe gazillions of years, there would be some real havoc to play because the sun would be pulled towards the Earth and we may get a very hot period of time. So let's look at a more recent period of time and some data that's probably a little bit more, shall we say, traceable in its accuracy. And we're going from 2010 again back to 1960. So there's a good 50 years here. It's a good period of time. If man has any effect on the climate, as you've heard, it's going to be occurring sometime in the latter portion, the latter 2/3 of this time. And what I want to point out here is that the temperature and the CO2 seem to line up to each other. CO2 is in black, temperature is in red. And yet, what's really happening is that there's essentially a 12-month delay. And other studies, this one particular one, further statistical analysis indicated 6 months. And other studies really are indicating somewhere 6 to 12 months. Now, this is a period of time that largely we've not seen, half this period of time is when we saw a temperature increase, and half the time we have not seen much of a temperature increase. So this is a good representation period of something that you would say shows variability. But in each of these cases that I've showed you, and this is just another indication of the same thing, temperature precedes the increase of CO2. That's rather significant. Now, this is what's called a scatter plot. To any of you in the semiconductor industry, you'd know this very well. This looks like your Dow Jones portfolio, whatever it might be. This is CO2 on the bottom, plotted against temperature on the vertical axes. Now, you look at that and you go, there's really not much of a correlation. And statistically, that's true. Statistically, that's true because the statistical parameter of fit or merit is near zero. So that says there's no fit. So in this period of time, something else is dominating temperature, and CO2 is not lagging temperature in this period of time. So again, complexity of the planet. So we have to now stop, pause for a moment, and you have to ask the question, do we have any role for CO2 in driving temperature? We're not done exhausting all the aspects of this question. But so far we've come up dry. It's a very small trace. It lags temperature. Most people would say, well, we're done, right? No, we're not. We've got to keep examining the science of CO2. Now, one of the ways to do that is to take one-dimensional models, which are basically regression models, statistical models, and take the past century. So we have data for temperature. We have data for all the solar cycles and intensity and so on and so forth. And we take all those models and we begin to analyze, can we find a role for CO2? So let's quickly go through about 6 of these models. First model is probably the most statistically meaningful. And what they did, these are very well recognized and respected climate scientists. This is not a semiconductor guy playing with a spreadsheet. These are very valid people in the industry. They're revered and peer reviewed and so on. And so what they came up with as far as the past century is that ENSO, which is basically North American ocean cycles, is along with volcanoes and solar activity explained the climate. Now, you probably have all heard, you should have if you've seen any of the material, that there's no way to explain the last century, the rise in temperature, without incorporating a strong component of CO2. These people showed that that's not right. They found it, and they found it to a much higher statistical fit than any of the so-called alarmist databases. I talked about Willie Soon, a Harvard professor, strong as nails. He's under a great deal of political pressure there at Harvard, but he is steadfast talking about solar activity, sunspots, and how that pertains to actual variation in climate. There's a guy named Weiss, did I get it right, David? That is taken for European temperatures 6 natural cycles and align them, and you can see the basic fit is pretty decent. You now have Svenmark, who's took a long period of time to convince people to fund his work, and he showed that cosmic rays, variation in cosmic rays can vary the amount. As you have more cosmic rays, you get more low-level clouds. Low-level clouds reflect sunlight, so the thermostat's turned down. So he showed that, in fact, that is indeed the case. And then there's another one that started to work and has done some work in the past year on neural nets and just looking at this giant piece of data from a big data standpoint. You've all heard about big data. Well, this is the attempt. And so the net result of all of these, none found CO2 in its total form. I didn't say ACO2, I said total CO2 to be a driver of climate. So we struck out again. So what have we learned? Okay, so let's capture that before we move on into some of the broader topics. CO2 is a trace gas. Anthropogenic CO2 is much less so. It's 3%. So CO2 does not appear to drive temperature, but the other way around. Is ACO2 a gangsta? Natural causes dominate from what we can see looking at the last century. CO2 science, I can tell you this by virtue of everything that we have studied. We have found so many questions that have not been asked. And I'm going to bring that theme up periodically now as we get into other aspects. So CO2 science is clearly not settled, despite the fact that it's supposed to have been settled. And it has not. Climate science has basically not received a very good scientific method. They propose, but they don't experiment. When the data doesn't agree, the data is wrong. So how good are the IPCC models? We're down to basically, relying on the IPCC models and any other predictions, which we'll get into, that might provide us insight as to CO2 or ACO2 is doing anything to the climate. So the key questions are, do the models work? What's water vapor doing? and so on. Because water vapor, as I indicated in the beginning, is a fairly significant part of the equation. So the key, and this is what we've come down to now that we've sort of taken CO2 and diced it into history and percentages, we've come down to the key question. Can a low amount of your CO2, and it's 0.0001%, can that capture enough heat in the atmosphere to warm the Earth's surface? Now you're kind of a bit skeptical, maybe too much data, or so we've got, and there's a precursor here that I have to tell you is that from the Earth's surface, the Earth needs to rid itself of energy. The sun provides us energy, it dumps energy in, which we'll talk about, and you have several opportunities from the Earth's surface to get rid of that energy. Evaporation is number one. That's the predominant one. Radiation of infrared is number two, and conduction, convection, number three. So it's a complex system. And so this gives you, and I'm going to make this easy to understand. You've got three charts here, all gases across the wavelength of IR. So this is the energy going out from the Earth's surface that's infrared. That's number two, not number one, but number two. And you're seeing all gases. So the all gases says that if the number is up here, it says that the energy is being consumed by the gases in the atmosphere. What does this say? The atmosphere is largely opaque. There's a window here which allows the infrared energy to just go to outer space. But look at CO2 relative to water vapor. There's some rather significant points that are going to relate to everything having to do with models. So under 8% of the total energy radiated from the Earth's surface is available for CO2. It can only do 1/12 of the energy. Water vapor is 20 times more effective at absorbing more wavelengths, and you can see that graphically. So it's the gangsta here. And so H2O is 100 times, to go back to the stats, the original stats on Earth atmosphere, the water vapor is 100 times more concentrated, has a higher concentration than the total CO2. And I want to remind you that ACO2 is simply a small percentage of CO2. So I'm going to present to you a conceptual model. And a lot of people would argue with this model, but I think as you begin to see this, and we began to think about this, it's not only a good indication of what's happening in the Earth, but it's also a good indication of what is not known about climate science. So here we are at the Earth's surface. We said three mechanisms of energy. I'm only going to talk about radiation in this diagram. But outer space, you've got to get the energy to outer space. And when you get the energy to outer space, it's there because radiation occurred at high altitudes. You don't have evaporation in the stratosphere. You don't have evaporation at the moon's, near the sun. So really what we're talking about is the open window that I indicated to you is about 20% of the total. So it's a lot more than what the CO2 can see. But the CO2 actually is 8% of the total, but it's captured, but then the so-called AGW, or global warming enthusiast, have that warming the atmosphere and not going anywhere. But in fact, I'm proposing that it actually is generating and interacting with the water vapor. What I didn't point out in the previous absorption curve is that the water vapor spectrum of absorption overlaps CO2. They share the same photons. So that's a rather significant finding. And so again, water vapor is just a lot more potent. So if you look at clouds, they really do matter. Now look at this particular event. If you can see it more clearly. The evaporation occurs at the Earth's surface. Water vapor rises, and it rises up to a temperature which is obviously decreasing as you go up. And you know this because you've all been on planes and they say it's minus 17 degrees centigrade outside at some altitude. So the water vapor goes up and it condenses. Now when it condenses, it releases a tremendous amount of energy. And the winds from the tropical region and the exhaustive energy into the atmosphere is occurring as a result. There's a great deal of things that are not known about this, and we hope to understand them a little bit better. But basically, what I just presented is outside the realm, even though as you look at these clouds, you know they're exchanging energy. It's outside the realm of AGW. So let's turn to IPCC, which is the organization that holds the modeling, holds the keys, drives a lot of the things that we've been talking about. So the question to the IPCC is, where is the water vapor? Now, IPCC says 77% of all gases in the atmosphere, they call them greenhouse gases. We take exception to that term, by the way. But 77% are due to total CO2. And water vapor is incidental, and it's somehow driven by something else happening in the atmosphere. So they assume that CO dominates energy. So I'm going to go through this rather quickly because I know I'm probably running a little short on time. Sun comes in, radiation out. There's something called back radiation, which is essential to the AGW computer models. And so you have things that effectively you come in with 163 watts per square meter, and you're generating from the Earth's surface 300 and, what does it say, 98 watts per square meter. Now this would solve all our energy needs, right? We just capture, we have 160 in and 398 out. It seems like if you had any thermodynamics in your education, you'd say, doesn't that violate the first and actually the second law of thermodynamics? And you'd be absolutely right. And the interesting thing is that Einstein would be arguing this in today's world. He would be arguing against this particular diagram. So there's some funny stuff going on here. So the conclusion is, for some of what we're going to see, we're about to show some results from the modeling, is that the IPCC model assumptions in climate physics seem to be wrong. So how good are the results? Well, here are the results. Now, in 1975 up to pretty close to current time, maybe a little couple years behind in terms of this diagram, but the thing is basically on the same kind of curve. Now, you'll see that the models are shown in red, the average of all these models, which they have a variety of inputs that they give it in order to try to find some way to be able to match the data. And what is not discussed in the literature is the mere fact that the model output over here seems to be fairly decently in agreement with the measured data. Well, it turns out that that's where the models were tuned to agree with the data. So we have to be careful. This is not a pristine model output. But we do have a period of time here in current time where we have a fairly flat temperature profile, which is real, despite the attempts to make it not. And we see something that's increasing rather significantly. Now, why is this the case? We're going to run through this rather quickly. The assumptions on CO2 forcing are simply incorrect. You see, clouds are not done well, and this is by their own admission. They cannot, in that cloud photograph that I showed you, there's no way the models could reproduce that. And they even say in their technical reports, we cannot do clouds. If you can't do clouds, stay home until you can do clouds, in my opinion. But it goes beyond that. Physics included are limited and sometimes actually incorrect. And there's compute limitations. You need a supercomputer that hasn't been invented yet to have enough clarity and resolution. And obviously they're not including variability in sun cycles and volcanoes and various other things that really do, as you saw, are statistically meaningful for the last century. So until we know otherwise, why aren't they meaningful for the next century? These models are not doing it. And they've all contributed to this bad result. Now let's look at two other aspects of the model so that you don't think that this is in any way cherry-picked. So if we look at the Corn Belt from 1900 to 2013, you can see the temperature that's measured for the Corn Belt. So this is rural, America. So there's no urban heat effect in essence. And these are the models that are predicting the temperature for that region. And you can see the deviation that's occurring. So this is not, predictions do not equal output. And the other thing that actually is something that is built into the models, there is something called a hotspot. It's hard to see in this display, but there's a hotspot up here at about 12 kilometers in altitude at the equator that the models require. In order to show the global warming that you saw in the previous chart, or in both of the previous charts, you have to have a hotspot at a certain altitude. And yet, when they put up balloon data, they measure it on satellites, they do everything they possibly can, and people have tried to justify the hotspot, but they haven't been able to do it. There is no hotspot. So this is a rather significant, negative as far as the models are concerned. Now, if I look at this eye chart, and there will be no testing on this eye chart, this is sort of a very simplified diagram of the atmosphere. And so you can ask the question, well, there's got to be, 102 computer models, three-dimensional computer models. Think of the money, and you guys have done the best job, by the way, in indicating where the money has gone. Think of the money spent on 102, models. This is significant. These are supercomputers running for days to create a data point. The models actually do not do any of these phenomena well. They don't show ocean currents, they don't predict rain, they don't predict ice cap performance, etc. So I'm running out of options here. Where are we gonna find? In essence, the models don't work well. In summary, it basically forgets the natural causes. It forgets that ACO2 is way down in the mud anyway. It overstates CO2 in its entirety. So why is this not common knowledge? Well, the mainstream media is keeping it quiet. Okay, so what do the people in IPCC think about this? I mean, these are career climate scientists. Trent Berth, who is a senior executive, if you will, in the whole IPCC, which is the UN Organization on Climate Change. Fact is, we can't account for the lack of warming. Says it, they fought like crazy. We have to wait 15 years. Well, they waited 20, no warming. We can't account for the lack of warming at the moment, and it's a travesty that we can't. Okay? Is he going home? Is he going to give us a refund? He says the following thing, but the data are surely wrong. Our observing system is inadequate. Now, I think Richard Feynman would come out of his grave on this point alone because he's an advocate for a good scientific method. This is not. So let's look at the current. We'll run through a couple of current temperature exchanges. You can see that in this period of time we had an El Nino. So it's largely attributed to that, as is this spike. And we went up in this period of time. People on the AGW side just said, we've got it. The pause is done. We're ready. We're ready to unleash the hounds and come up with a new Paris Agreement, whatever. But November came down to 0.36 from 0.6, one of the largest drops in annual temperatures across this record. Still have warm spots, but the recovery is happening. In the news this morning, polar maximum is hitting the East Coast. They're going to get record lows throughout the rest of the winter. You had record lows in Chicago, New York, and Boston, I think, while we were in Africa. So is the pause continuing? Nobody knows. Nobody really knows. And the people who put this chart together, this is by far the best satellite data, say that. And let's take a look at, and I seem to, more on temperature trends. So let's look at other temperature trends. It's got to be something somewhere here to show that humans are doing something wrong. This is the South Pole is not warming. You can see this trend exists for almost 30 some odd years. This is pristine station data in the United States. Pristine meaning that it's validated. It's not near a piece of asphalt. It's not near a city. These are pristine data points that are verified, people have confidence in. Do you see variability in the temperature, but do you see a trend? This one is actually the balloon data that I showed you briefly in comparing model versus actuals. That indicates that, this indicates rather that the balloon data, which is very accurate data, it's self-calibrating, it goes up in altitude, shows you basically what was represented in the satellite data. There is no suddenly mysterious data set that could be validated that's showing global warming. Okay, so predictions that are made beyond the model outputs. So we're going to go into, well, we couldn't find it in the models. We couldn't find it in the amount of CO2. We couldn't find it in the history, and we can't find temperature correlating with CO2 properly. So we really do need to ask Al Gore for his Academy Award back, I think. So here is an example. The poster animal is the polar bear. And Susan Crickford is an expert in polar bears. And what was happening in around this time period is this is the North Pole, and there was predicted to be thin ice in the North Pole. So the Arctic region is thinned, and it has indeed thinned. And so this is back, I think, maybe 2005 or 8 or something. Actually less than that. It's in the last decade. And so the polar bears were expected to decrease in population. Well, what ended up happening was it all increased except the one with thicker ice. So they actually went against their assumptions. And because, very simply put, is that polar bears can hunt very nicely in the summertime with thin ice. They just say, come here, seal. So here we are. We've got the thinning of the ice. Ice is coming down even more than predicted. But they don't talk about the fact that the polar bear population has actually increased. And Michael Mann, who is a figure that you will continue to see, who is one of the, I think, to be short, is one of the true frauds of any climate advocate. He said, we are the polar bears. We are the bears. If the bears go, we go. And of course, we have to come to Al Gore for predictions, because he's totally precious. His movie, we could go on and on about that alone. But in the next 10 years, we're in trouble. Reach a point of no return. The point of no return, you've noticed, is keeps moving out. And in 2008, we're going to be done. The Arctic, sea ice, which has gone away naturally, by the way, periodically. It's gone away naturally, periodically. Not so often the Antarctic. But it'll be gone in five years. And for comparison's sake, but to cap it off, the polar bears do have something to say about that. When Al was born, there were only 7,000 of us. It's a shame, but there's only 30,000 that remain. So these predictions aren't really working so well. Greenland, if you look at the record of Greenland from this year, the coldest temperature ever recorded in July in the northern hemisphere was recorded this year in Greenland. You won't read that in the New York Times. And the ice this tends to show you the incremental ice. This is the record from last year and this year up to a certain point in time. And you can see that it's actually way above average. What ends up happening on the polar caps, if there's more serious melt in the polar caps, the refreeze is way above average. So it melts and refreezes. It's commonsensible in a certain sort of way. And this says basically the same thing. Now, we'll talk about sea level. Carl was talking about, this program was talking about sea level. And we chose to take this chart, which takes you back in time, to show you the variability that has indeed occurred. So this is us today. And this goes back thousands of years. Now, again, this is where Homo sapiens started to evolve in the form they are today. So this is a significant amount of history. And this is measured at various points. However they measured it, they were able to do various indicators. But look at the scale on the right-hand side. This is not 20 inches. This is not 20 feet. This is 20 meters. This went down 140 meters. This shows you the natural variability of sea level. So what can we say about sea level today? Well, ABC predicted in 2008 that New York City would be underwater by 2015. Last time I checked, it wasn't. And in fact, really, and I see this every week. Someone writes me an email and they say, did you see this? And I go, no, I didn't, but I'll tell you that's wrong, and that's wrong, and just be done with it. So it's about 1 foot per century, and that has been pretty consistent. But the capper is, what's happened over the last year? This is satellite measured data It's fairly accurate. It's a summary of the level of sea level. What's happened in the last year is sea level has stayed constant. Interesting. Not relevant necessarily, not conclusive. And so what we're seeing is that in some areas of the world, this being in Quebec, Canada, the sea level is actually going down. So you're seeing variability in different regions as well. Again, complex system. Beware of summary data points, the theme of this talk. So climate, let's sort of take a real broad stroke before we move on into other, policies and politics. Sea levels, glaciers. Glaciers, by the way, most glaciers on Earth are no older than 4,000 years. So 4,001 years ago, a lot of glaciers weren't here. And you've seen, I think, somewhere in the neighborhood about 10 to 20 meters increase in sea level from what it is today. So long and short cycles. The ocean has a cycle that lasts for 1,000 years. You've heard of El Nino and La Nina. That's one of the shortest cycles. There are cycles that go for a long period of time. And again, I want to reemphasize, the models are not accurate. They don't predict much of anything, and clouds especially. And clouds are a very essential part of the climate. Laws of thermodynamics cannot be dismissed. Thank you, Einstein. He made a very strong point of this. Water vapor dominates as an IR-absorbing gas, but never gets the credit for it. It's really the gangster here. So let's move quickly into politics and policies, because I want to touch on some of the origins of these things, because it certainly it'll be something that you will learn from. And can we control the climate at what cost? Now, you can actually go off and do some data gathering on your own. It turns out the Cato Institute has a page, and you can go to their site, do a carbon calculator search, and you'll come to this page, and what it says is that you can play God for a moment, CO2 God. And you can say, I want to reduce CO2 by a certain percentage, and I want to have it occur at this sensitivity, and I'm going to see what temperature I can create as a result of that. I can tell you in short that if you wipe out the United States, the temperature at the end of the century, by this model, which is an EPA government-approved model, by the way, that the temperature of the Earth by the end of the century, this century, will go down by 0.25 degrees centigrade. Now, I usually try to demonstrate anybody that shifts their weight from one elbow to the next has now demonstrated 0.2 degrees centigrade. This isn't measurable. So, okay, so we're here, we're kind of stuck, we can't find a reason. As many people say, I hear you, Terry, not going to happen, not going to be a problem, but shouldn't we do something just in case? Right? The precautionary principle. So let's take a look. So what policy choices do we have? Do we innovate and rely on future technology? Or do we do what you guys hate the most, and I do too, more government? So what about the Paris Agreement? That was a good shot. Everybody signed it. It's purported by so many people, the Pope included, to be essential to the future of mankind. We're going to boil the planet. After all, the human species is extinct in two decades. We've got to do something. So let's take a look at what the Paris Agreement really meant. Now, the UN was ecstatic by the signature of people signing, particularly the United States. Obviously, I won't go into the details of how much liability the U.S. was trying to acquire. But economists have looked at it, and you could say the total cost of the Paris Agreement, economic growth, money out, et cetera, would be in the neighborhood of about $360 trillion. About 100 plus, 180, 60 trillion from the U.S. alone. And along the way, we'd basically be in a situation where a lot of people, particularly in this study, where people in Europe would be dying as a result. So, okay, so we spent the money. We got to really, but it's worth it, right? We got to save the planet. What do we get as a result of this? Now, this is temperature above pre-industrial, and this is all the way through the end of this century. Now, notice the three curves that, the do-nothing curve is what's called 8.5. I won't delve into that, but that's a wrong set of assumptions, but that's the one they use. So it's the worst case scenario. So if you do anything to reduce CO2, it should really be showing you the best payback. But in actual fact, what it does show you is that just Paris gets you 0.05 degrees centigrade. You can't measure it. But if you do Paris extended for 70 years, because it goes through 2030, you get 0.17 degrees centigrade. Nowhere near the 2 degrees, or limiting the growth of temperature down to 2 degrees. So this is another bad deal. And this is analyzed, I'm probably not going to go through this, but these are, as Matt Ridley said, the various policies that have already been put in place. And you begin to see that ethanol kills people, biodiesel, it costs too much, promotion of diesel cars, toxic waste, wind power, you're killing birds, but you're also spending a lot more money than you thought you were, and solar farms and renewable energy and so on. Renewable energy is, you might have seen a statistic, and there was a recent article on this, seeing that renewables actually generate 13% of the world's energy. You think, whoa, I missed something. Where did we put all those solar panels? It turns out that 10% of 10 percentage points of the 13%, or the majority of it, is due to the fact that the world is burning wood, which is considered to be a renewable. So you have to pay attention, students, you have to pay attention to how people are using their terms. But the neglect of more serious environmental problems is indeed an issue that we should be concerned about. There's a lot of things happening in the West Coast, managing forests, and I could take you through Huddart Park next to our house in Woodside, and I can show you all the wood that's not been maintained. It's sitting there waiting for the next fire. Okay, so IPCC quickly. Beginning of IPCC was started back in the 70s. One of the key ingredients in this push towards making sure that people knew that they were creating too much CO2 was driven by a guy by the name of Maurice Strong, no relation to Michael Strong, by the way, but Maurice Strong, and he had the following things to say. He said, what if a small group of these world leaders were to conclude the principal risk to the Earth comes from the actions of rich countries? His answer is, in order to save the planet, the group decides it isn't the hope for the planet, isn't it the only hope for the planet, the industrial nations collapse. It is our responsibility to bring this about. Now, isn't that a clear statement, and one that you're surprised he made? Because most people who are going to read this are from an industrialized nation. They're not going to give him the credit card. Now, Maurice Strong has a very interesting history. He actually absconded with about $500,000 worth of funds from, I think, the IPCC. He went to China, tried to establish a car company importing cars back from China into the United States with his good buddy, business partner, George Soros. Maurice Strong came from the Club of Rome, so this is all very Malthusian in its origin. So AGW likes using the phrase, so I'm going to use it back to them. AGW, worse than we thought. AGW, anthropogenic global warming. Declaring and prosecuting deniers is not science. Imagine 26 state AGs out to arrest me. I say, bring it on. So there is no consensus. And I can tell you it's 97% of a select group of a select group of a select group. There is no consensus among scientists. In fact, really, a lot of the data that I've given you, a lot of the analysis that I've given you, is actually resulted over the course of the last 2 to 5 years. So there's a lot of people that are really working on their own nickel, not taking grants, and actually giving up association and employment in the academy. AGW is now a huge business. As I said earlier, you guys have the best data on that I've seen. Clear intent is more centralized power and redistribution of wealth. They don't make any bones about that. So to conclude, isn't it easier to fool people than to convince them that they've been fooled? Is that not the case? Boy, you suck into that little download of a belief system, you're not letting go anytime soon. And I think what David and I have really subscribed to is the theory that for here we are not afraid to follow the truth. If it takes us to global warming, fine. We're there, we're going to be all over that. So far, as you can see in this presentation, we have not found one scintilla or parts per million justifying AGW as a theory. That's a pretty bold statement. But we have no axe to grind. We have actually no academic papers to justify it. We have no affiliation to align ourselves with. We tolerate no error, any error, as long as reason is left free to combat it. And I think the kids and the grandkids that are generated by this population rely on this. So I want to thank you for your attention.